Hi everyone, I'm Shao Feng from Shanghai Jiao Tong University and Tsinghua Institute. Thank you so much for giving me this chance to talk about our recent study about neutrino mass measurement with cosmic gravitational focusing. This paper is in collaboration with Pietro Pasquini and my student Liang Tan. So I would first overview the current neutrino mass measurements and the future prospects, and then introduce a third way of cosmological measurement using this cosmic gravitational focusing. So first, as we know, neutrino oscillation is a macroscopic interference. It can measure the neutrino mass square difference. Here I use two neutrino oscillation scenarios to illustrate the idea. The oscillation probability is a function of the mixing angle and the mass square difference, delta m square. Then from the oscillation frequency, we can interpret how large is the mass square difference. And this is actually the first new physics beyond the Stein model. So currently, we have already measured two mass square difference. One is between M1 and M2, that is smaller at the level of 10 to minus 5 electron volt square. And another one is between 3 and M1 or M2, and this value is around 10 to minus 3. Currently, we just measured its magnitude for the size. The mass hierarchy is the thing has to be determined by Juno. But unfortunately, we cannot measure the absolute value. But we can roughly estimate the typical value is probably the square root of this mass square difference, which means it should be like a sub-electron volt scale. So in order to measure the absolute value, we can use the beta decay. Neutrino, if it's massive, it can take away a little bit more energy. And then in the electron endpoint, electron spectrum endpoint, there would be some tiny difference. For example, if you have this 1 electron volt scale, then this endpoint is feasible. Of course, the total energy is quite large, around like 20 keV. So this 1 electron volt square can only lead to like a 10 to minus 4, 10 to minus 5 difference. So it is a very, very difficult experiment. To fit the endpoint, we need to parameterize it with both endpoint energy and mass square. And you can see that currently the sensitivity is roughly 1 electron volt, a little bit better than that, but still it's quite rough. And if you see neutrino is a bit decay, then in principle, that can also help us to identify the absolute mass, especially if the effective mass falls into this final region. Also, it seems like a very unfortunate for neutrino decay measurement, but it has multiple benefits. First, the absolute mass should be in this range from like 3 millielectron volt to 6 millielectron volt. Another thing is it would form this Marana triangle. From the sides of the three sides, actually, we can interpret the two Marana faces simultaneously, which would not be possible if we really see this neutral decay. Anyway, this hasn't been seen yet, so still we need to wait. Another thing is for atomic process. When it jump from this excited state to the grounded state, not just one photon would be emitted, but also two neutrinos, neutron pair in the final state. Since atomic process is typically at electron volt scale, the neutron mass would be important, especially in the photon spectrum. Actually, we can scan the structure and find that there are several sections. Between different sections, there are several turning points, and these turning point positions are actually determined by the neutron masses. So by just scanning the spectrum, we can precisely identify what's the mass eigenvalues. Unfortunately, this is highly suppressed because this vertex, effective vertex, is mediated by heavy gauge bosons. We need double enhancement from the superradiance and also the macroscopic coherence. So still, that's in the future. And in addition to these experiments on Earth, we can also use supernova neutrino burst. It mainly comes from the neutralization. And we can see this peak in electron flavor neutrinos actually would be very sharp. And the typical time scale is millisecond. And then we use the time delay and the time structure. We can try to put a constraint on the mass. For example, for the projected sensitivity at the dune, it can reach sub-electron volt scale. But we need to wait for next supernova. And then another one is a cosmic neutrino background. Actually, it contributes a very large flux, and its temperature is quite low, like just 1.9 Kelvin. That corresponds to 10 to minus 4 electron volt momentum. So if neutrino mass is really the size of the mass square root of the mass squared, and then it should be larger than this temperature. Neutrinos becomes highly non-relativistic. Its energy is dominated by its mass. And this would have several consequences. First, we can use the Ptolemy experiment to measure the inverse beta decay neutrino scatter with tritium, and then emit one electron. Since neutrino now appears in the initial state, its mass would bring some energy to the final state electron. And we can see beyond the beta decay endpoint, we can have this small peak, and the distance is determined by the neutrino mass to m. Of course, this difficult is also very difficult, especially the cryogenic technique. So all these previous methods, either the sensitivity is still quite rough, or the needs for future technological improvements, or the happening of supernova, for example. Currently, the cosmology provides a very precise measurement. One thing is the CMB. Massive neutrino can decrease the CMB power spectrum, and this can reach sub-electron volt scale. And the contribution of neutrino appears like a sum of their masses, linear dependence. Another thing is the large scale structure. Massive neutrinos, their free stream scale is not that large. This would enhance the power spectrum. And we can see this it's quite sensitive, actually even better than the CMB measurement. Can put an upper limit on the mass sum, that's 0.13 electrovolt. And here I would introduce a third way, the cosmic neutrino fluid, and its diffraction by the dark matter halo. So the basic picture is like this. It's something like a stone in water flow. When the cosmic neutrino fluid flows through or pass by the dark matter halo, its path would get deflected, its trajectory would get deflected by the dark matter halo's gravitational potential. So this is kind of like a bending. And suppose we consider neutrinos with the same velocity, and they would bend towards each other. So these would have several consequences. First, let's try to use the point mass to get a description. Then it becomes like the interaction between just two point particles, dark matter halo in the center and individual neutrinos. And the diffraction angle is expressed in this way. So roughly we can imagine that this diffraction, if there is no diffraction at all, delta phi should be pi in the framework around the dark matter halo, with dark matter halo at the origin. From the infinity past to the infinity future, the angle changes by pi. And then if the deflection happens, they would introduce a small correction. Of course, if neutrinos are massless, actually, this deflection can also happen. It's kind of like light bending around the sun, which was used to justify the GR theory. But if neutrinos are massive, the effect would be significantly enhanced, because currently CUB, the temperature is just 1.9 Kelvin, that's 10 to minus 4 electron volt. And if the neutron mass is above this value, then it can get significant enhancement by this n over p. Then it's not just a small factor, and it's kind of like a squared term. With this diffraction, then you can imagine that the neutron momentum would change. Suppose finally the magnitude, when it goes to the infinity distance, the magnitude will change, but the direction change. Then in its original direction, the horizontal direction, the momentum actually reduces. But for the vertical one, also it grows for neutrino fluids. Actually, it has symmetric distribution. So not just a single neutrino, but it has symmetric cancellation for the vertical component. Only the horizontal one would survive, and the survived amount actually is reduced from the original one. And in this way, the momentum in neutrino is reduced, but we know the momentum should conserve, since the dark matter halo would get some extra momentum. So momentum transfer would happen between neutrino fluid and the dark matter halo. And because it's dynamical friction. That's the first effect. And the second one is the focusing effect. This is essentially like a lens, the focusing. The neutrino density actually would grow after passing by the dark matter halo. And this density fluctuation can be readily obtained with the help of Boltzmann equation. This is quite a generic feature. It applies not just for point mass case, but also for continuous distribution. Since enhanced density would affect the galaxy formation. So at higher overdensity, actually it's much easier to form galaxy. And this dipole structure, actually it is a dipole after we subtract the average density. Dipole structure would appear in the in a more transparent way in the momentum space if we do Fourier transformation. Then we can see that since the Fourier mode, if you take a complex conjugation, actually it would receive a minus sign. So that means it has only imaginary part. So in addition to the average density, this the dipole density fluctuation would appear like imaginary thing. And this kind of thing can be extracted from the galaxy correlation functions. So the basic picture is we have cold dark matter overdensity fluctuation and also the neutrino overdensity. The galaxy overdensity is a combination of these two. It's not a simple sum, but actually it's linear function. In front of it, they have bias. This is a B factor. They are different. Of course, finally, when we do the oscillation, we need to consider the redshift space distortion SD effect. But finally, what we want to extract is the correlation function between galaxies over some distance. This is delta G alpha and delta star G beta. Alpha and beta should be different. They should belong to different galaxy categories in order to have different bias. This is delta B. So you can see this imaginary part actually is proportional to the bias difference. And the other part comes from neutrino. So it is important to have different categories of galaxies. And for the galaxy distribution, including its number density and the bias, actually can be readily predicted with halo mass function and halo occupation distribution, HOT. This is for the BGS category. For the typical surveys such as the DESI survey, BGS contributes the largest amount of galaxies as a bright galaxy sample. So we actually divide this major category into two according to their mass. And then we can see that they have some different bias. Of course, we also consider other categories like ELG, LRG, and QSO, but they wouldn't contribute that much. After considering these galaxy creations, they mainly appear at the scale from like 10 megapc to 100 megapc. If we go to too large scales, then the average bulk velocity would decrease. If we go to too small scale, then the volume is not large enough. We don't have that many galaxy pairs. So finally, it appears in this range. So I won't go through more details. I just show you this result. So one important thing is the dependence on neutrino mass is actually force power. So that's quite different from CMB and the larger scale structure. So on this plot, the blue region denotes the normal case, the normal ordering case, and the red one for the inverted ordering. So the further regions are for the current cosmological constraint and oscillation for the at this 95% confidence level. So you can see that for inverted ordering, this 95% confidence level limits can reach something like 21 milliseconds. And if we consider the same situation for inverted ordering, you can see that if we consider the cosmic gravitational focusing, actually the sensitivity is already above like 2 sigma, even for vanishing mass. So it is a significant improvement. Of course, we can also here we show the plot with true value and the test value. So you can see that the current one, the red one, actually comes from the CMB and the larger scale structure. On this mass sum, it can reach something like 30 milli electron volt. It is still a very wide band, but if we consider the focusing effect, then for focusing alone is the blue one. You can see that in most of the parameter space, actually it's already better than the existing one. And if we combine everything, then the black one is much smaller than the red curves. So the band, the distance between the two curves. So you can see that with this third one, it can further enhance the sensitivity for these cosmological measurements, especially it provides an independent way of doing the measurement. And I just want to mention that in China, we have this China Space Station Telescope, which can also do this kind of galaxy survey to constrain the neutrino mass. And so that's what I want to say. So third cosmological way of measuring neutrino mass by using the cosmic gravitational focusing. And the basic idea is the neutrino fluid would get focused around the dark matter halo, forming dipole structure in the density in the overdensity, neutrino overdensity, and this would affect the galaxy formation. And in order to extract this information, we take the galaxy creation function, especially the imaginary part, which directly corresponds to the neutrino gravitational focusing effect. And this effect actually depends on the mass as the force power, which is quite independent way from the CMB and the larger scale structure. Okay, thanks.